let's give you an
Yeah. Okay. So, Oliver,
Yes.
Yeah, I have a couple of questions regarding the maze balls.
Yeah.
I guess that a compulsory question is that if you have compared the low frequency gap or reflectance with a common Helmholtz resonator, just a spherical ball with one hole or holes in symmetric places, you know, because in the end, this negative bulk modulus happens as well for a common sphere with a hole, but maybe you can lower the resonance. But have you compared how?
I just calculated the frequency that you would have for a hollow sphere with a single hole, I think.
Mm-hmm.
And it was, well, of course, it depends on the hole size, so it's a bit difficult to say. But say you just remove the internal part of the sphere and you just leave the 8 holes. I think I found that the frequency rose by roughly a factor of 5.
All right.
Which is a Helmholtz resonator. So the basic just lowers your frequency for you, but it doesn't do anything else. So lowering the frequency is always good for people who want to do metamaterials, because you get much longer wavelength for the same size. So your object starts to become metamaterial-like to a good approximation. So maybe that's the advantage of having. Also, if you want to stop sound with a sort of small object, yeah, it helps. Of course, you can stop sound with a single hole in a opaque screen, so with a membrane inside it. So I think it's more of a academic interest rather than practical interest.
I see. And I guess that the number in this picture you saw, you have like I don't know, 8 layers of the maze inside. I guess that is difficult to have more than that, right? For the
it says n equals 8. I
8.
think this refers to the number of segments, but the layer is 1, 2, 3, 4, 5, 6.
Yeah. So because
I get that difficult to do more. These people had only 4. 1, 2, 3, 4. 1, 2, 3. Actually, only 3. So, okay, their complexity was so many holes here, like 20 holes instead of our 8 holes. But then our complexity is a few more layers here. So I can't say ours is totally simple to make.
I guess. And well, obviously you have only 5 possibilities to make these maze balls, which are the 5 solid platonic solids, right? Like the tetrahedron, the octahedron, icosahedron, and so on. I think it should be nice to compare the 5 geometries. And also it gives you a very nice title to your paper, right? Platonic
dodecahedral structure. Yes, of course, you could. Yeah. It has to fit together in a sphere. So yes, if you just round it off, it would be nice to compare them. I guess you could do the same thing. Of course, you can do the same thing with empty spheres. Just the holes in the outside. The only thing about the maze ball is it lowers the frequency for you, but.
Okay, so sorry, I'm just using all your time, so maybe someone has another question besides me.
I have a question on the phoxonic metamaterials, Oliver.
Yeah.
You mentioned that when you were looking for grant money, you first thought about going to optical frequencies and gigahertz. Did you think of a specific type of experiment, maybe like a Brillouin light catch scattering?
Yeah, I tried to propose in the grant to do this one, this gold pads fishnet. I tried to propose fishnet. I thought maybe if you took an optical fishnet like this one, which is already a double negative optical metamaterial, that you could somehow incorporate a gigahertz acoustic metamaterial by adding some, soft oscillators or something. But it's very difficult process-wise to do that. And also proving the thing is, if you read these papers, how they proved that this was a double negative optical metamaterial, it's a very, very difficult measurement. It requires phase measurements and very difficult optical interferometric techniques, and it wasn't easy to do. So it's not like in the microwave range, you can build one, you put a source, and you make a lens, and then you have a focus point, and it's very easy to observe. But in the optical regime, everything is submicron, and it's very complicated to prove this. Also, you can't make the lens thick enough to make it into a decent lens, because you can only have a couple of layers and then it absorbs. So it's very absorbing in the optical regime. So it's very difficult to demonstrate it at visible optical frequencies. Even near infrared would be very difficult. So that's why we just gave up and went straight to microwave frequencies.
Okay. I have another question regarding the solution that you have proposed with the silicon rubber. So when you added it, it seemed to me that you got some kind of a small band gap around it was around
here. But not so small, actually.
Yes.
I mean, this is 0 here. I'm sorry that the numbers are so small, but this is 0, and this is about 2.4 kilohertz here.
Yeah. This is like the phononic band structure, but also in the electromagnetic dispersion relation, you had a small band gap.
This one is not so important because it's not actually necessary for the double negativity, because the original research, it was like this, no band gap. So it was joining up, and it was all designed to have this wonderful, so simple properties, and also impedance matched, of course, to air. So the ideal structure, in fact.
But actually, it seems to me that if you measure the electromagnetic and the phononic band gap at the same time, well, you have a demonstration of a phoxonic crystal at those frequencies, which has not been done a lot of times, I would say.
Well, I don't think anybody's bothered to try this because it wasn't clear why it would be interesting. But anyway, I just thought it was fun to try. I think it's possible to do the negative modulus as well with a bit of ingenuity and make a quadruple negative. I think it's possible, but I don't have a concrete proposal at the moment. But I think it can be done.
Okay.
You just fiddle around with it, You tried not to ruin the electromagnetics and just add bits here and there. Yeah.
Okay. All right. Thank you.
A little bit, as I apologetically said, it's not completed research because you need to parametrize the effective physical parameters. So you need to tell people exactly what is the effective modulus, density, permittivity, and permeability. You have to calculate it. And to do that, you need to do an N cell an n+1 cell simulation and then derive it from that. And it's actually a lot of work. It's a really big sort of, takes a long time, this project. Yeah.
Right.
So it's not like so easy to do all that. I mean, beautifully, rigorously, and convince everybody. Yeah.
Yes, please, Sebastian. Yeah.
Yes, I have a question actually regarding this. Oliver, can you show back this slide?
Yes.
Slide 43, I think it's 43. Yes. Sorry, maybe it's my misunderstanding, but there is some discontinuity in your dispersion curves. You know, at the gamma point, in the middle.
This is strange. Yeah.
Yeah.
I don't know what happened here.
Yeah. And this happens also in the lower part of the spectrum. Look, you have you can see some bands. They seem to cross. You know, the third. Yeah, here, this point. Yeah.
I'm a bit.
Yeah.
You have to look a little bit carefully at the.
It's the way. Yeah, I think you get the answer. It's the way you describe your Brillouin zone in 3D that creates perhaps this.
I would like to think so. Yes.
But no.
But I should look into that.
No. I don't understand, because when you reach the gamma point from any direction, this. No, I don't understand.
This point somewhere on this diagram should be. I think there's a mistake or something funny happened here. It should be continuous, shouldn't it?
Yeah, it should be.
Yeah, sure.
And you have the same kind of weird phenomenon, on the other edge. The next, you see as well these two. There is also a discontinuity, like
I don't think I have another graph, do I?
Yes. So there. So
that's a little bit suspicious. I agree. Sorry, I have to look into this.
Yeah.
This is just a PowerPoint slider.
No. I just wanted to ask a general question here.
I can show you there is a conference paper where we didn't try to be so shall we say ambitious, and just give the simpler one small section of the dispersion relation. So I don't really vouch for the complete spectrum that I showed there, but at least over gamma to X, everything looks reasonable. Okay.
Yeah, of course. And I have another question. Regarding your ball. So it's very really fascinating. So you have 8 parts, and in fact, so they are kind of glued together. And so this junction between the 8 parts of your ball, what is the role played by this junction? You know, between the.
Well, the junction is basically just screened. It's screened by a 1 millimeter thick layer, I think. I think you can see here that D/2, D is 1.5 millimeters, and there's a D/2 here. That means you have to double it. So there's 1.5 millimeter screen between all these 8 layers. That is enough to stop the sound.
I'm very sorry. In fact, what I mean is that, so when you assemble them, it's like, so you have 8 parts, haven't you? And each part is
in 3. So
but on
24 parts.
But what is the role played by the glue? What is the role played by the glue in terms of the acoustics?
I think there's some.
Isn't this similar to rubber? Isn't it similar to role of rubber, like a small rubber?
this material is very hard material.
Yes, and
Like
the
epoxy,
glue is
but-
soft. The glue is soft.
Well, the glue will harden, you know, very hard. So it's like super glue type stuff. So it's it's sealed, properly sealed. Okay?
So for you, it's really clamped. It's really clamped for you. It doesn't. There is no way. There is a slow motion or
it's
something
clamped.
like that.
It's properly clamped. Yeah, very
Okay.
very strongly clamped.
Okay.
Only when you try and saw the thing in half,
Okay.
sometimes it becomes a little fragile because
Okay.
each of these little these sections here, they're only connected on one side,
Okay.
and two sides are open. So any attempt to remove this top surface, like
Yeah.
if I removed all of this would fall off. Some of them would fall off.
Okay.
Yeah.
That's very interesting. I mean,
Actually, the ones that you can see here would fall off. This one would fall off, this one would fall out, and this one would fall out because it's only connected to this one side. Yeah.
Oh, it's a wonderful object. I mean, a very, very interesting object. Thanks a lot.
Well, I think Ting Zhang was very, very brave to try to make it because it's really difficult to make. Yeah.
Okay, thank you, Sebastian. More questions? Yeah, I guess that regarding the Sebastian's comment, maybe what I mean when sound propagates through air, any solid is essentially a hard boundary. However, if we were studying the modes, the elastic modes of the ball itself, then the contrast between the rubber and the material and so on could be more important. But as long as the excitation comes from the air, it's really difficult, as far as I understand.
But what I thought is that the pressure wave might couple to this kind of interfacial layer.
Okay.
Might couple to the structure, and then this would propagate as a shear inside the body, and then somehow convert back again as a pressure wave on the next junction. You see what I mean? And then you would have a coupling between pressure in air and shear inside of the body, perhaps. I mean,
yeah,
that's what I had in mind.
Well, yeah, maybe it can happen, but it depends at which frequency do you want to observe that. I have no idea. I cannot make any guess. So, any other question?
Actually, we did. I think we did the simulation with the actual materials, and it didn't change anything very much. So we did the simulation with the epoxy, the effect of the epoxy in there.
So you did not extrude the part of the material. You did not consider it as rigid. You really have in your simulation a material. Okay, that's a full model. Okay.
Not in the one I showed you in this talk, but we checked that it didn't make a difference. Yeah.
Okay.
I believe we did that. I'm pretty much 99% sure. Yeah.
Okay, thank you. I have another question.
One last thing, but obviously this would be very different in water. We all agree that if it would be a underwater pressure wave, it would be totally different, the story.
Yeah, in underwater would be a completely different story. So because the acoustical properties of the materials could be quite similar, for sure, right?
In water, it would be terrible. Yeah, it would.
Yeah.
You'd have to use a solid which was much more rigid than water, but that's quite difficult because water has quite a high. Well, it's 1,500. It's already 5 times faster than the sound velocity in air. So starting to be difficult to have hard boundaries with the case of water. Yeah.
Yeah, maybe you have to go even up to lead. I remember to have done some simulations, but I guess that a 3D printing machine working in lead is more expensive than the one you have, right?
That's a bit tricky. Also, the mass problem, because the water would engender, it would definitely engender a motion of the solid. It would be difficult. Of course, you can increase the pressure of the air up and up and up until things start to happen. I mean, or you could put argon in there, or there's all sorts of things you could do, of course, but yeah.
I mean, of course, it would be very interesting for you to try the experiments in for underwater acoustics, because I mean, you would really couple the pressure wave with the shear wave inside of the solid, and so, I mean, you would have a fluid-solid interaction. Maybe this would generate some very interesting physics, you know. Maybe
yeah, maze ball underwater. I mean,
yeah,
it would be
yeah.
fun because it would be very easy to make the structure. And actually, what you're suggesting is, when I first saw this space coiling, I immediately thought, let me do a simulation for a solid maze, because I thought this idea might work in solids, but I forgot that sound goes round corners relatively easily when you have an air-filled waveguide, but when you have a solid waveguide, sound is very highly reflected at corners, and also mode conversion. So actually, if you try to make a maze that's actually where the sound is traveling in the solid, it doesn't work. And we tried to make a prism like that, and the sound was absorbed at the surface, and it was a complete disaster. Yeah, basically, yeah. I might be able to show you a movie of the abortive attempt to try to make a solid space coil. Yeah, this was so disappointing. But sometimes one learns from one's mistakes. But yeah, really, that was a real disappointment. So if I just where is it? Yeah. I can show you just for fun what happened. Sometimes it's good to see when things went wrong, because everybody's always presenting science when everything's gone right. But sometimes you learn. Well, everybody knows that. Sometimes you learn, like penicillin or something, you learn quite a lot sometimes when things go wrong.
Yeah, but it's difficult to convince an editor to publish a paper where all the things were wrong. But maybe it should be quite useful for some people.
Okay, just a second. I'll show you something funny. This one, yeah. Okay, so can you see this picture?
Yeah.
This was the coiled solid material. It was like I think it was just a slab of something.
Can you show it full screen, Oliver? It's not on full screen.
Full screen. I can just make it bigger like this. Wait. Can you see it bigger if I go like this?
No, it's just an icon. We can just see an icon.
Yeah.
It's not coming?
No.
Because this. Okay, I can remedy that. Just a second. I'll put it on a PowerPoint. That will be better. It's a bit time consuming, but so yeah, okay. Well, I didn't think carefully before. So I'll come back to this PowerPoint now. So can you see this screen?
Yeah.
So that is the wave trying to make its way inside a coiled metamaterial, but it's a solid one. It doesn't get anywhere. And okay, so it's a bit like, can you see this one? Mm-hmm. It's a bit of a structure like that with a a kind of soft layer and a hard layer, I think, or vacuum, maybe just vacuum in between or air in between. This part is solid, but it doesn't penetrate. And a whole wall, it just penetrates about 3 or 4 unit cells, like that. So it's very, very, very disappointing. And if the unit cell looked a bit like this. So the black regions are removed and the white region is solid. But it doesn't work.
So looking at it, it's a Dickney-like structure. So it's the effective properties are isotropic. It's chessboard-like, isn't it? You have this rotation by pi by 2 and 1, so it's isotropic. I mean, it satisfies the Dickney-Keller's theorem.
So if what I'm trying to say is, this is solid, everything is solid, but the white regions are removed. It's like I think it's a thin plate where you just drill some slits, okay?
Yeah. And
you just leave the parts. But if this was air, there would be no problem. It goes through. Okay, as you know, there's some damping, but it doesn't work with solids. So you suggested doing it with liquids, but you may run into similar difficult problems. Yes, I guess.
Yeah, probably. Yeah, sure.
Yeah, you may run into difficult problems. Yes. I think.
Okay, so well, I think it's time now to finish the session.
Okay.
Thank you very much, Oliver.
Thank you.
I probably will send you an email with some idea regarding this maze balls, because I was working with some analytical models to simulate these structures, and
that's nice.
That's nice. It's not that difficult actually if some conditions are satisfied. I will tell you, because even if it's a three-dimensional problem, if you find an analytical expression for the scattering properties, that's a very huge advantage. And I have some notes on my box, so I will write you later, okay? Together with some questions about picoseconds ultrasonics as well, if you don't mind.
No, I don't mind. No, on the contrary.
Okay, excellent. Thank you very much.
And thank you very much, everybody today. And thanks to Bogdan and Sebastian and Kumar. What's his name? What's your name? Madik Kumar. Yeah. Thank you very much.
No.
Bye bye.
Yeah, thank you, Oliver.
Guys, and thank you so much for this closing talk of this season of metamaterials. I mean, it means a lot to us to have Oliver, Danny as a chairman and speaker today. It's really fantastic. Thank you so much. It goes straight to our heart. Bogdan, do you want to say a few words, a few kind words to because after all, you are the main man.
Yeah, I'm not the main man. Every participant is the main man of what we succeed to do in this 2 years. It was a great thing. Thanks again to the today's speakers, and let's hope that we can catch up and do even better things next year. Yeah, thank you all.
And please, guys, if you think of any good people to give some webinar for the next season, starting in September, get in touch with us. I mean, we would be very keen to have, some suggestions of potential speakers.
Yeah, maybe we'll organize another kind of roundtable for some discussions at the beginning of the year, and we are open to any suggestions or things to make this similar, but not only, even some other materials we can put online or the disposition of everyone. More accessible and visible for everyone.
By the way, Oliver, do you plan to be in UK in the beginning of September?
I think that is unlikely because I just got back from Europe a couple of days ago. So maybe the next trip to Europe might be next year, though. I'll tell you, though, when I come.
Because we would very much love to have you as a, in-person speaker for a seminar or something like that. Yeah.
That would be a pleasure, but we have to get the right timing.
Okay. Yes.
Thank you.
I think that will be also a case of not falling into, the infernal spiral of COVID again.
That's
So,
important.
I was told it's very hard to go to Japan right now, no? Oh.
It's definitely very hard to go to Japan. Yeah. They still aren't open. Except if you're scientifically invited, it's okay. So, yeah, if you're invited for you can.
And there is some form of quarantine if you, I guess.
No quarantine. No.
Okay.
Usually.
Okay, guys, I have to leave because they have closed the air conditioning here at the university.
So the temperature is rising.
It's becoming like a black body, so that Okay, has to be really nice to see you again. And well, we keep in touch for sure. Okay.
Okay. Thank you so much, Daniel.
Yeah.
Thank you.
Bye, Daniel.
Bye, guys.
Thank you.
Bye, everyone. Bye, all.
Thank you. Okay. So is it time to say goodbye?
Yeah. And good night.
It's a pity. Okay. Good night.
Yeah. See you soon.
Yeah.
Bye-bye.
See you. Good night. Yeah. Bye.